Alright, so I have started to stream on YouTube's side. It's a little early. We got about 2 minutes and a half before the class starts. And the first thing I'm going to do is to talk about one solution of the homework assignment, the program that is due at 5:30 p.m. today. And then we're going to move on and talk about the concept of a stack frame. And also, how we can systematically access items on the stack so that we don't have to move a register around just to get to items, which is what the previous lab is suggesting you to do. But that's the easiest way to do it. It doesn't involve a lot of extra labels. So that's what we'll be getting onto today. All right. So it looks like we got maybe about half the class online at this point. And there's no one on YouTube side, so that means everybody is on the side of Discord. Cool. All right. Yes, go ahead. I will certainly try, but I cannot promise anything because question number 1 is still kind of it's going to take a long time to grade that one. Question 2 is not as much, it's not as bad. Question 3 is not as bad, but I will certainly try. Mm-hmm. Mm-hmm. Hmm. Well, the assignments are easier, so I can, grade those a little bit faster. For the most part, you can compare your answer to the key and, get a I hope you can get a good sense of, how you're doing in the test, by comparing your answer to the key. Um, and also, if you know the material and you explain those things well, I think you probably get a good sense of that. Um, so Well, I'll see. We'll see how fast I can grade those questions and homework assignments. Mm-hmm. Yep. All right. So it is time to start. So I'm going to get started with. We'll start with dealing with the program that was due at 5:30 p.m. I haven't really checked how many people have turned it in and how people are doing in that particular one. Um, but I think it's probably important to go over the solution of that particular program, and then we'll move on to what a core frame is and how to work with that. So one thing I do want to point out is it is kind of important. No, let me take it back. It is extremely important to review the material, including, the sample programs that I did in class because I attach the source code of the sample program at the end of a class, for a reason, because I want you guys to have access to the source code so you can annotate the source code so that, you can insert your own words to explain, what each line is doing in those programs. So when people do not download those programs or may not be aware of those programs, I worry. I'm not concerned about, my work is wasted because it's not, okay? But I'm much more concerned about, people are not understanding that these are very important resources for studying in this class. All right. Q3. Okay, so To explain Q3, you can watch my video because I prepared a video this morning to explain the answer of question number 3. So even though every single one of you has a slightly different case of the value, the approach of doing it is the same. So all you have to do is to watch the video that I made this morning, and you will know what you should be able to work it out, what the answer is supposed to be and what type of steps I'm looking for. So I hope that answers the question in the text channel, which is, to me, it's also a little bit troubling that people have not watched that video that I linked in the text channel of today, like from this morning. So it is important to do that. I can do that. It's just it would take me some coding in order to have one customized solution for your specific case. But for the most part, it really is just substituting a different value instead of whatever I used in this morning, which I think is 327 divided by 4. You guys just start with a different value, a different numerator, and a different denominator. The denominator, I think, is 4, 8, and 16. Those are the 3 choices. And then the numerator has a lot more choices because I think the way I did it was to choose 3 ones out of 7 bits, and then the bit 8, which is the 256, is guaranteed, and then bit 0, which is the one is also guaranteed. And then in between there are 3 bits that are, so depending on which version of the test you get, you just get a different value. Okay, so I don't think it is too hard to to follow the instruction that I gave you this morning and figure out the answer for your own test. And obviously that's my opinion, and people can certainly disagree. All right. So getting back to the function call thing, so the key concept of the function call module or lab is to emphasize that the stack is being used by the subroutine to get the parameters from the caller and also to store the local variable. So what I'll do is I am going to skip to the code, okay, that is specific to the swap subroutine. So I cannot remember which one it is. I'm just gonna be scanning a little bit. All right. I think it's question 4 that has the code. Yep, there we go. All right, so question 4 really is the key. I'm giving you the main subroutine already, but the main subroutine is here just so that I can set up the stack. By the time I call the subroutine, I clean up the stack afterwards. So the main part that you need to do is to implement the swap subroutine, understanding that everything is on the stack. It is important to understand that we are not, okay, let me emphasize, we are not, NOT, using registers to communicate between, to send arguments from the caller as parameters into the callee. That is not how we do things, okay? We are going to use the stack for communication. The only time we use a register to communicate is when the subroutine has a return value, and in that case we use register A to specify the return value from the subroutine back to the caller. Alright, so knowing that, and also knowing that we push arguments on the stack in a reverse order, which means the last argument is pushed first, which also means the last argument is going to have an address on the stack that is higher than the earlier arguments. That is the standard, okay, and it is also illustrated in this particular example. So my focus is just going to be on how to implement the swap subroutine using TTP-ASM, and I'm going to use the approach that was illustrated earlier in the same lab, which is basically using a register to move around on the stack so that we can access different parts of the stack so we can get the parameter and we can also get to the local variable. Alright, so with that said, I am going to switch to a dumb terminal. And alright, so we can make a new tab and put it over here. Okay, so first thing first, I'm going to copy and paste the C code. So this way I can have a starting point. So here's the dumb terminal. I will make it as large as I can in the recorded area. So this way I can fit more text. There we go. I'm just going to check, make sure this looks good. Yep, looks okay. Alright, so here is swap.ttpasm. Oh, wait, I have to do one thing first. So I'm going to copy and paste the C code into the assembly code file. So this way I can easily cross-reference between the C code and the assembly code. Alright, so now we are ready to implement the subroutine. And obviously the syntax checker is not happy about this because this is C code and not in TTPASM. So first thing first is to comment out every single line, and that's just by inserting / at the beginning of each line. And because I'm using Vim, I can do it with a command, which is really kind of super handy. Alright, so with that done, we can now specify the entry point, which is swap, and also specify how we are going to get out or return to the caller. The code to exit or to return to the caller is pretty much the same 3 instructions all the time, because by the time we get to the end of a subroutine, the stack pointer should be pointing to the return address, which means an LDB D is going to retrieve the return address and put it into register B. And then we can do an increment D to deallocate the return address from the stack because it is already retrieved. It doesn't need to be on the stack anymore. So by quote unquote deallocating, all I'm doing is to move the stack pointer. I'm moving the bookmark that is marking the divide between which part of the stack is in use and which part of the stack is not in use. So now we can do a JMPB to jump back to the caller. Alright, so now we can go back in. And the first thing we want to do is to figure out what is the stack going to look like at the entry point of the swap subroutine. So I'm going to use this notation where entries to the left-hand side have a lower address compared to entries to the right-hand side. So the last thing that we push on the stack, which is currently pointed to by the stack pointer, is the return address. So I'm going to use square bracket to enclose the item that is currently pointed to by the stack pointer. And then the other entries, now because the left side are for the entries with a lower address in RAM, so the right hand side are, as I put more items to the right hand side, those are the items with a higher address. So in that case, PTR1 is immediately on top of return address, and then PTR2 is immediately on top of PTR1. This is what the stack looks like at the entry point. In the C code, I have a local variable t, and that is not allocated by the caller because the caller has no idea how many bytes should be reserved for local variables. So in order for t to exist, in order for the stack to have room for t, we have to decrement the stack pointer. Okay, so we have DCD, and then at that point the stack is going to look like this. So t as a local variable is going to be allocated right below the return address. And then the stack pointer is no longer pointing to the return address because it is decremented into the location. Now, what would be the value of t? Well, it's uninitialized because all I did was to move the bookmark down by 1 byte so that we are claiming this byte is now a part of the stack that is in use, but we didn't do a single thing to initialize it. So right now, even though the stack pointer is pointing to local variable t, the value of t is unknown. It is uninitialized. All right, so I'm checking the text channel, making sure that we don't have any questions. There are 2 people apparently using YouTube. Oh, actually, I take it back. There are 4 people using YouTube. I would just kind of make the suggestion to switch to Discord because the lag time on Discord is much shorter. So it's easier for me to answer questions and easier for you guys to ask questions too. But once again, that's a choice that each person is going to make. All right, so this is what the stack looks like after the decrement D instruction. So now the first thing we need to do is try to implement this instruction. So when you see an assignment statement, this is actually a statement because of the semicolon at the end. Without the semicolon at the end becomes an expression, but now it is a statement. So as an assignment statement, I personally always try to figure out the right-hand side, which is the value that is going to be used to update whatever is specified on the left-hand side. So my first job is to figure out what this expression is going to, what is the value of this expression. So in order to figure out this expression, I have to get to PTR1 first. So to do that, I'm going to utilize a second register. So I'm going to use CPR-CD to copy register D to register C. If anyone is asking, how do I know which way the copy works? Are we copying from D to C or are we copying from C to D? The answer is in the opcode table. So look up the opcode table, that will answer that specific question. Now, if for people who are inquisitive and go like, but that's just, a description. I want to know exactly how CPR works. That would be the circuit diagram of the processor. And I am expecting you guys to be able to read the circuit diagram and also be able to basically specify in an instruction like this and analyze how the pathways are formed when this microcode slice executes in the processor. So that is an expectation that we all should be able to do that now. Alright, so what is the effect of this particular statement? Because C and D are now the same, they're both pointing to local variable t, so I'm going to use round parentheses to surround the item that is pointed to by register C, and I'll give you a key here as well. Okay, so I'm going to say, this is pointed to by register C, and then this is pointed to by register D. So now we have a legend. Okay, so that when we read what is going on the stack, which register is pointing where, now it should be relatively clear of those things. All right, so first thing first, we still have to get to PTR1, and I cannot move register D. Yes, go ahead. Is there a question? Oh, okay, not a problem. Alright, so what we need to do now is not to move register D because the stack pointer, it has to stay in place unless you are sure that you don't need the item below where the stack pointer is pointing to. And right now we need every single one of these items. We need T, we need return address, we need PTR, and we need PTR1 and PTR2. So, but we can move register C around because register C has no special meaning. So we're going to do an increment C, and whoops, I said C and then I typed D. So we have increment C, increment C. So okay, if I want to do this, like blow by blow, step by step, this is what it's going to look like. Okay, because register C is now it's pointing to the byte representing the return address, and if I increment it one more time, then it's going to be pointing at PTR1, like so. There we go. All right, so C is basically the address of parameter PTR right now, and I'm not going to comment this code because I want you to review the video and then comment it. Okay, so I'm only going to verbally say it in the video, but I want you to be doing the annotation. So at this point, register C is the address of PTR1, which is great. Okay, we are getting closer to what we need, but it's still not what we want. So the first thing we need to do is do LDA or B. So right now, both register A and B are available. So I'm going to use register A and then indirect C here. So what is going to happen after this? Okay, I am going to give you the actual comment in this case. So register A is the value of PTR1. Now, when I say the value of PTR1, I am not referring to what PTR1 is pointing to. I'm referring to the pointer itself. And then after that, we look at the C code. Okay, we are not interested in PTR1, the pointer itself. We are interested in what it is pointing to. So now we need another LD, to indirect one more time. And this time we're going to use register A, like that. So that A is now whatever PTR1 is pointing to. So this is my right hand side. On the left hand side, we just need to store into local variable t. So we look at variable t and go like, it is all the way back here. So we got two ways to do this. We have two ways to handle this. We can basically just say, it's still pointed to by the stack pointer, right? So we can just go ahead and say, that will do it. Okay, because the stack pointer is pointing to local variable t at this point. So that is one way to do it. Okay, all right. So moving on to the next statement. This time we have to figure out PTR2 and basically what PTR2 is pointing to, and then use it to update whatever PTR1 is pointing to. I'm not going to optimize and reuse registers between statements, so I'm going to recompute everything at this point. The only thing I'm going to reuse is register C. Register C is now pointing to PTR1. We need to get to PTR2, so let's go ahead and increment C. So now what the stack looks like is register C is now pointing to PTR2, which is sitting on the stack. That is not what we actually need, because we need what PTR2 is pointing to. So once again, we need two dereference in order to get to that. The first dereference is going to get us the value of PTR2 into register A, and then the second one is going to retrieve whatever PTR2 is pointing to. So this is now the entire right hand side. Now we need to get to the left hand side. We need to start with PTR1, and register C is now pointing to register 2. If I decrement it once, it will point to register PTR1. So we have a decrement C at this point, and then what the stack looks like in terms of what C and D are pointing to is now going to look like this. All right. And PTR2 is still on the stack, it's just not pointed to by register C anymore. So at this point, we go like, but we don't want to update the parameter itself. We want to update what the parameter is pointing to. So that means we have to first do a dereference to get to the value of PTR1 first, and then we want to store to wherever that thing is pointing to. So now we want to store to whatever register B is pointing to, because at this point register B is PTR1, and the right hand side is already in register A, so this will complete the operation of the second statement in the swap subroutine. If you have any questions, don't hesitate to ask. I would suggest to you to use the text channel to ask questions, or use the voice channel in Discord to ask questions. Alright, so we're almost done. We are now getting back to here, and the first thing we need to do is to retrieve the value of local variable t. That's pretty easy, because the stack pointer has been pointing to local variable t the entire time, so that's pretty easy to retrieve. So we just say LDAD. That's going to retrieve the value of local variable t into register A. Now we need to get to PTR2. And we can see that the register C is pointing to PTR1, so we have to increment it to get to PTR2. So increment C, and I'm going to update the map. Okay. And now it's pointing to PTR2. All right, so okay. I thought I saw something on the text channel, but I did not. There's nothing happening there. Okay, so now we have to do a LD. Cannot use register A anymore because it's being used for the value on the right hand side. So I'm going to use register B. So register B is now the value of PTR2, which is a pointer to where I want to store the value. So I need a ST instruction now. So store to whatever register B is pointing to, and the value that I want to store over there is in register A, which is representing the value of the right hand side. So that should do it, right? Then we get to the return statement here. Oh, that is not going to work, right? Because in order for the return instructions to work, the stack pointer has to be pointing to the return address at that point. And we can see the stack pointer is still pointing to local variable t, which is of no use to us anymore because we are done with the subroutine. So what we need to do now is to do an increment d to deallocate the local variable. And by that I am meaning that this is the stack pointer is no longer pointing to the location corresponding to local variable t, and now it is pointing to the return address on the stack. Alright, so I'm seeing some activities in the text channel. I don't think the stack looks the same based on the main code. The values of x and y are stored on the stack. That is correct. That is absolutely correct. But I passed the address of x and the address of y as PTR1 and PTR2. So x and y are local variables of main, and the main code is responsible to push the address of y and the address of x on the stack, and it does that. So by the time we get to the subroutine, we do not know x or y anymore. We just know the parameters of PTR1 and the parameter of PTR2. Does that work, Paul? Okay. Okay. All right. Cool. All right. So I claim this code works. Okay. And of course, I'm not going to just leave it as that, because that would be irresponsible. So I'm going to copy the code of main from the lab so that we now have a complete program. So I'm going to copy all this code into the program that I just wrote, which is here. So I'm going to use cat. Ooh, this is going to be tricky because I want to put it as the first part. Well, I can always put it as the second part and then do a jump. Okay. So greater than is appending. So it doesn't destroy the existing content of swap.ttp.asm. It just appends whatever that I'm pasting in now to the end. Okay, so there we go. And so when I look at swap.ttp.asm, I have the swap subroutine as the first thing, and then we have the main entry point over here. So I'm going to keep the main as the way it is. Instead of moving things around, I'm going to insert a no-op here and a JMPI to main, which is something that we talked about already. The no-op is needed in order for the trace to work, and then JMPI main is needed because otherwise it will start executing with swap as a subroutine, which is not what we want it to do. So in the main subroutine, it is quite commented already. So I'm not going to spend much time to talk about the main subroutine, except for what we are pushing on the stack. So what we're pushing on the stack, we're pushing the address of y on the stack, and then we're pushing the address of x on the stack. The way x and y are allocated is we allocate for local variable y first, and then we allocate for local variable x. Alright, so at this point I'm going to, well, first save the file, but the second thing is to encourage you guys to figure out a way to document what is on the stack and where are those items on the stack. Okay. Well, bad grammar. Where those items are in the stack. There we go. All right. So I'm going to use a spreadsheet, just because that's the quickest and easiest way to make a table, which is what I want to do. So under Office, I have Calc. There we go. Which is nothing more than just a little spreadsheet program like this. And let me increase the font size a little bit. There we go. Come on. There we go. Alright, so location FF, is the last location. It is allocated for local variable y. So if you look at y, it should be here. And I'm going to use main y to indicate this is local variable y of main. And then we decrement again in order to allocate for local variable x. So local variable x is at location 0xFE, and that's the x local variable x of main. And then after that, we do the initialization. So after the initialization, the value, the content at this location should be a 7, and then the content at this location should be, let me see, a 3. Okay, so a 3 is going to x, a 7 is going to y. And then after that, we push the value of y on the stack. So the location corresponding to that is FE on the stack, but this is basically the PTR2 parameter of swap, and the value of that is 0xFF. Alright, so we got some text going on. Oh, okay, my face. Right. Okay, I am going to... Now let's move this down a little bit until I can't do that anymore. Okay, there we go. I think that is good. Just a little bit lower. There we go. And move it this way a little bit. Okay. That looks okay. Alright, so now we have, then we push the address of x. The address of x is FE on the stack. So at location FC, we are pushing parameter PTR1 of the swap subroutine, but the argument that we use to specify that is the address of x, which is 0xFE on the stack. And then we push the return address, so that is at location FB. That is going to be my return address. And I'll just make it clear to main. That really should not be needed because we only got one subroutine call in this case. Alright. And then the exact value, I don't really know. The assembler, would know, but I don't really need to know that. So basically at the entry point of the subroutine swap, okay, at the entry point right here, this is what the stack should look like. And the stack pointer, which is register D, is pointing to this location at the entry point of swap. Okay. So in the subroutine, we are basically going through, we are using register C to move around on the stack, retrieve the value of those individual bytes, and then dereference these things so that we can get back to the original value of the local variables of main. That is what the swap subroutine is supposed to do by using the pointers, of the arguments, by using the parameters as pointers. All right, so we got Paul typing. I'm gonna pause a little bit here. I mean, the rest of the class, you're more than welcome to kind of chime in if you have questions. So to write this program, okay, so let me see. Doesn't LDAA mean you're working with the values of x and y rather than the pointers to them? All LDAA is going to do is to go to the location the register A is pointing to, retrieve that value, and then use that value to update register A. That's all it is going to do. So it doesn't really matter, whether a register has the address of a parameter or whether it has the value of a parameter, which is a pointer type, so that we have to dereference it one more time to get to what the parameter itself is pointing to. Alright, so I think the best way to understand how this program works is to run it through the trace analyzer. Okay, so we're going to do that. Let me go back to here. Alright, so this is in temp folder. So what I need to do is to go to my river spider subfolder and run my script. So submit. Oh, by the way, I also updated the script so that it can handle basically a much larger source file as well as the trace. The trace can get really large even if the source file is tiny. Alright, so we submit temp swap.ttpasm like that. So this one will update the shared assembler that you guys can all see. So if you point your browser to the assembler, you should be seeing the updates like right away. Alright, so it looks like it's done. We go to the assembler window, which is here. Oh, great. Okay, let me sign back in. We can still see it, because it's read only at this point. Well, I suppose that's okay, but I probably don't want to be signed out, because with that script I don't really need to sign in. I don't need to change the spreadsheet manually because the script is doing it. Alright, so let's check the source code first. That is what we had. Okay, so the source code is correct. And if we look at analysis, let's see whether this is doing what it is supposed to do. Okay, so we're going to do some spot checking here. Remember, the first thing that usually check is at the end of the trace. We want register D to be 0, and we want the last instruction to be a halt instruction. So that's what we want to check first. And let's check. Register D is indeed back to 0, and then location 32 in hexadecimal should be the halt instruction. So we go back to the Assemble tab and check that. So location 32 is indeed the halt instruction. So that is good so far. Okay, the next thing we will check to see if the program works or not is to see whether the content of local variable x and y are indeed exchanged or not. And according to this map, okay, that I drew earlier, y started off with a value of 7, and then x started off with a value of 3. So when the program is done, they should be exchanged. So let's double check that first. Okay, so we want to check the value, how we update location in RAM, and we update FE to be 3. That is correct, right? Location FE is supposed to have a value of 3. We update location FF to be 7, and we can see how location FF is supposed to be 7 here. And at the end, when the program is done, we think those two locations should be exchanged. So we want to look for updates of location FE and location FF and see if those are updated correctly. So right here we see location FE is updated to be 7, and over here we see location FF is updated to be 03. So the program did in fact exchange the values of local variables x and y. They belong to main, But since I passed the address of those local variables of main into the subroutine swap, now swap has access to those locations as well, and that's how this program works. Now, if you were to trace this C code, not the assembly code, but the C code, it would have done exactly the same thing. And you could have done that using online GDB, or using GDB on the command line, or use code blocks. Do whatever you want, with your favorite debugger. But the idea is you have to rely on a debugger, set up breakpoints, single step through the execution of the program, examine, the parameters, and it also examine the value of local variables that belong to main along the way, and you will see that the C code will do exactly the same thing that I have described here. Now, obviously, when you're using GDB, you're going to end up with a 64-bit address, so all of these things will be like super long. For the most part, you only need to care about like the least significant 3 or 4 digits in hexadecimal. The rest are going to be pretty much the same, throughout the execution of this program. All right, so I'm going to pause and see if there are any questions at this point. So if you have questions, please go ahead and use the text channel. All right. So I'm looking at the text channel. I am staring at the text channel right now, burning a hole on my monitor, waiting for questions. I can certainly post the code. Let me do it here. Okay, so I can just post it here. And it is swap.ttpasm. There we go. And there you have it. And I'm going to pin it too, so it's easier for you guys to access it, because I know there will be more text messages along the way. All right. So remember, I'm giving you the text, the source code, because I want you to annotate it. Okay, meaning that you probably want to insert your own words as comments, so that you can explain to yourself what is going on with each and every single statement or instructions inside swap. Main is really kind of documented already, okay, but you might want to read and understand that part too. But the really important part is to understand the swap subroutine, and every single instruction is important. So there's nothing, should not skip anything, okay? You really should not skip anything, and basically annotate every single instruction. The spreadsheet I'm not going to post. I suppose I can just okay, this is what I can do. Hold on a second. You guys have access to the video, right? And I know how effectively you guys can work with your computer to do stuff like this, but I'm going to make it easier. There we go. So I'm putting a little snapshot of the table that I created using the spreadsheet in the text channel, so you can also refer to that. The idea is when you write your code, you should be able to create or annotate what is happening with the memory locations before you run the code, because that's how you can test whether your program works or not. Is you have in your mind an understanding of what is supposed to happen, and then you compare to what is actually happening in the trace. If the trace deviates from what you're expecting, then we might have an issue. So you might want to explain that and go like, was my expectation wrong because I misunderstood what the program is supposed to do, or did I implement the program wrong so that the trace is disagreeing with what I thought should be happening on the stack? that is how we debug programs, not just assembly language programs, but also in C++ in your other classes, including Java too. I mean, Java does the language makes no difference whatsoever when it comes to the important steps of debugging a program. And if you have never been taught how to debug a program, well, guess what you're going to be doing for your almost entire career as a developer. If you become a software engineer, you may not be debugging as much. You'll still be spending, quite a bit of time debugging. I hope that's not too discouraging. Some people compare debugging, to using a toothbrush to clean a bathroom. I look at it differently. I look at it as, playing Sherlock Holmes, which is fun. A lot of fun. Especially when I'm debugging someone else's program. All right, any questions? Yeah, go ahead. Yeah. Yep. That is correct. Well, you still have to dig into those locations, even in regular C code. The idea is when I implemented the assembly code did not care about who is calling or whose local variable we are dealing with. So let me go back to the source code first. All right, so when we get back to the source code, in the swap subroutine, C is only moving around within the memory locations that belongs to the subroutine. In other words, it never made any assumptions of who's calling me, and where the local variables of my caller are located, because all of those are communicated through PTR1 and PTR2, which are parameters, and those are legitimately things that a subroutine has access to. Yeah, so it does have some aspect to scope. Okay, so since I talked about how to understand this program using just GDB and regular C, let me just kind of go back to that point, because I want to make sure that you guys have the tools that you need in order to do the additional homework assignments from here on, because we'll be doing a lot of this stuff, except it's going to be recursive, and with recursion, it's not really more difficult. It is more difficult to debug. Okay, so understanding the debugging process is very, very important. All right, so I'm going to use this as an example, and I think in the lab there is the C code. So let me go find that first. I might have backed out already. Nope, it's here. Okay. So this code here is directly copy and pasteable, except we need a pound include in the C code. So let me just do that, because I want to illustrate what I meant when I said what I said earlier. So this is swap.c, and I hope you guys already understand at this point that C is pretty much a subset of C++, which means everything that I have talked about up to this point in this class should be something that you understand already from your CISP310 class. So we'll pound include stdint.h, which is where the names uint 8_t, those names are defined in this header file. So at this point, this program should be compilable. So we'll do a gcc-g to include the debug information, the symbol table, -o to swap, and then swap.c is the source code, and then gdb swap dot, oh, just regular swap. There we go. All right, so I'm going to put a breakpoint in main and then put a breakpoint in swap. So when we run the code, the first thing we do is to stop in the main subroutine. I'm not really concerned about whether x is getting a value of 3 or y is getting a value of 7. I just want to know where they are. So I'm going to print the address of x and print the address of y. And then single step. And then now we're going to get into the swap subroutine. So when I single step one more time, we're now in the swap subroutine. In the swap subroutine, it has no scope access to local variables x and y of main, because x and y are, as I said, local variables of main, so swap has no access to those particular names. But swap still has access to the locations, because the address of x, yeah, the ampersand is a little bit dark, it's hard to see, and then the ampersand y are the addresses of x and y, and they are passed to swap. You can see how the parameters, ptr1 as a parameter, really is the address of x, and ptr2 is really the address of y. So there we go. And when we perform these operations, now this is the interesting one. Line 7 is the one that changes where ptr1 is pointing to. So if I single step, okay, I'm just single stepping it, and I can now print where is ptr1 pointing to. It is now pointing to a value of 7. So how do I know at this point that local variable, which location is it? I just changed whatever ptr2 is pointing to, and ptr2 is pointing to y. So how can I confirm that local variable y of main is indeed changed to a value of 7? This is also why it is important to know how to do a backtrace. So in a backtrace, we can figure out how we got to this point. In other words, it will give us the history of all the calls that led to this point. So we can see that main is frame number 1, and now we can say frame 1. That just changes the context. In other words, I'm not changing anything. There are no value change of the program. I'm not proceeding. I'm not single stepping. I'm just changing the scope of the programs, so to speak. But it is a dynamic scope because we are referring to a particular invocation of a subroutine. So we are now back to main, and in the scope of main, I can print y because y is a local variable of main. And we can now confirm that y has indeed changed its value to 7. So that is the effect of this statement here. So this is what I'm talking about when I said, you can use GDB to help you understand the C code so that you actually understand the behavior of the program before you even attempt to convert the code into assembly code. Because if you don't understand the C code, how it is supposed to get things done, or the constructs in C and C++, then there's very little chance that people can translate that code into assembly code. And even if they can go through some translation process, it will be impossible to debug the program without knowing the behavior of the same code, but in C and C++. Y was initialized with a value of 3, I think, or 7. I cannot remember. Oh, right. Okay, yeah, ptr1 is going to be the one changed, and ptr1 is x. So Paul is correct. So at this point of time, y has not been changed yet because y is pointed to by ptr2, but x being pointed to by ptr1 is changed. Thank you. Very good. All right. Well, thank you. All right. So use these resources. Okay. If you don't want to install code blocks or GCC on your computer, this can all be done using online GDB, which is the web resource. You don't even have to sign up for an account to get this done, because online GDB also exposes the command line option of using GDB, and all you have to do is to type exactly the same commands in online GDB, and you can accomplish the same thing. All right. So are there any questions up to this point? So I'm not only illustrating the solution to the swap subroutine, but I'm also giving you suggestions of how to approach writing code at this point, because it's not just a matter of copying and pasting. Okay, you really have to understand the concepts in C first, and then you have to understand the concepts in assembly language programming, which means you have to really understand what each instruction is doing in order to put the whole thing together. So there are a lot of pieces that we have to connect. All right. So any questions? No questions. Okay. If there are no questions, then we are going to do the same thing, but this time I'm going to use a different approach to write the same subroutine. Okay. So I'm just thinking, is that what I want to do? Because I'm thinking, recursion would actually be more helpful to illustrate the concept of a frame. So let me think about this a little bit. What I want to do to illustrate the concept of a frame. Okay, we'll use recursion. Alright, so we already talked about recursion like really early on, when we first introduced the idea of how to call and return. I talked about recursion already, relying on only a global variable in order to decrement it until we get to 0, and then we stop doing the recursion any further. So if you cannot remember that I said that, you might want to go back to the previous videos just to refresh your memory. So what I will do now is not to rely on the global variable, because now we have already talked about the concept of return value and parameters and local variables. So we're going to do that. So we'll do another recursion program. We'll do it in C first. And we'll include stdint.h and have the return type as int8_t, so that's signed. Whether it's signed or not really is not important because of the range of value that we're going to use to test this program. And it's going to take one parameter, which I will call x. And it's going to have a local variable, which is int8_t. We'll call that, I'll call that v. And we'll say v equals to, I'm just trying to think of a useful thing for this subroutine to do that would still require the use of a local variable. All right. Okay, I can do this. So we're going to say v equals to, okay, so we'll first use a conditional statement to determine whether we need to perform another recursion or not. So when we say when x is 0, then we don't do any further recursion. Otherwise, we're going to do some further recursion. So this is also something that I'm also kind of teaching you guys how to think in a recursive way, is to think about when do I stop, okay? When do I say, okay, this problem is simple enough that I can solve it right away. I don't need to call another, I don't need another invocation to solve the problem. So in this case, I'm just going to say, this is not a very good approach, but I'm going to do it, okay? So because it's not a good approach to have a return statement inside a conditional statement, it is always better to have a single return statement at the very end. But I am going to, I'm sticking with what I think is right, okay? So I'm going to say v equals to 1, and then at the very end, I say return v. There we go. All right. So what about the else? Else is going to be, so let me first describe what I want f to do, okay? I want f to find 2 to the power of x, okay? So when x equals to 0, I'm trying to figure out what is 2 to the power of 0, and that is just 1. What if x is greater than 0? I'm not going to deal with fractions, so x cannot be less than 0. So if x is greater than 0, then the first thing I'm going to do is to say, let's go ahead and figure out what is f of x minus 1. And then we're going to say v plus equal to v, because that's the same thing as v equals to v times 2, which means now we have f of x minus 1 times 2, which means we have 2 to the power of x minus 1 times 2, which means we have 2 to the power of x. So that's a very long and convoluted way to figure out what is 2 to the power of x, but it illustrates the concept that I want to illustrate. So in main, I am going to have a local variable just so that I can store the value and reflect whether the subroutine is working correctly or not. So we have int 8 underscore t. We'll call this p, okay, for power of 2. So we'll say p is f of 3 should be enough to illustrate the concept, and then return 0. So we can see again, this program has no printf, has no cout whatsoever. So the only way to see whether this program is working or not is to use a debugger. Alright, so we now use Gcc Debug, includes symbol table information, specify the executable file's name, and also the source code. There we go. And now we gdb recursion. There we go. And then we put a breakpoint at the entry point of the function f. And we want to list main so that we can see if there's anything we want to stop at. Nope, nothing. So we'll go ahead and run the program. R for run. So now we are at the first invocation of f. Now BT will tell you how we got here. It's telling me that in main on line 23 it made a call to f, and that's how we got to the first invocation of f. And if you want to single step, you can go ahead. So single step, it got to the else case on line 13, and now we are performing a recursive call of f. Continue execution. This is the second invocation of f, which is on top of the first one. So the first invocation of f is saying, I cannot solve this problem by myself. I'm going to have to call another subroutine to figure out what is 2 to the power of 2, and then I'm just going to multiply that value by 2 as my own return value. That's how recursion works. But BT is really helpful because now it is pretty clear that we have 2 invocations of f at this point. So main call f the first time, and then from inside f it calls f again, but this time the parameter is different because the first parameter, the parameter of the first invocation is 3, the parameter of the second invocation is 2. So obviously 2 is not 0, right? So we single step, it's going to perform another recursive call, and this time f is 1, which is also not 0. So now we continue execution again. Now it is 1. So when we do a backtrace now, we have 4 invocations of f with the parameters being 3, 2, 1, and then all the way down to 0 in this case. Now because x is 0 at this point, it will stop the recursion. It's going to go to the then case of the conditional statement, which is going to say, oh, we know what is 2 to the power of 0. It is 1. Okay, so that's the return value. It goes to return v, which goes back to, now at this point, if I do a BT, we still have these 5 frames on the stack. But as soon as I single step this particular return statement, it's going to go back to the previous frame. So let me go do that. And, oh, not yet. Okay, do another single step. So now we are down to the, back to the previous frame on line 14 of subroutine f. So at this point, if you were to say, okay, show me what is v, it is 1. And we are about to double it because we are about to execute v plus equal to v. So it's going to be doubling the value of v. So by the time we get to return v, v now has a value of 2. So when it return again, okay, we do another backtrace. We have now only 3 invocations left on the stack. And if I were to print what is v at this point, it is 2. Single step, single step. Now v has a value of 4. So I think you can kind of see how this works, okay? Because each invocation will just return the value of the recursive call times 2 as its own return value. So by the time we get to main, okay, I'm going to fast forward a little bit here. So when we get back to main, which is here, the local variable in main, which is p, should be 8 at this point. So we'll print p, and it does have a value of 8. So that's the behavior of this code in C /C++. And we haven't really touched a single concept in assembly language programming at this point. All of these concepts are just regular C, C++ programming concepts. So now, now that we understand how this program works in C and C++, we'll go ahead and try to implement this in assembly language. So let's quit the debugger, and we'll go ahead and look at the C code and look at the assembly code at the same time. So this is recursion.c. Oh, I need a dash uppercase O to split the screen horizontally, so that we can look at both the C code and the assembly code at the same time. There we go. Alright, so we'll deal with main first. Okay, main is the easy one. So as usual, no op, jmpi to main, and then we'll define main here. Oops. There we go. So main does have a local variable p. So now we are going to be more systematic. Okay. So instead of using a register and using increment, decrement, move it around the stack so that we can get to the item that we want to get to, this time we're going to be much more systematic. So we want to see what main, from the perspective of main, what the stack is supposed to look like. Okay. Now, because main is not called from someone else, it doesn't really have a return address from a caller, because there's no such thing as a caller to main, not in assembly language programming like in this class. But it does have a local variable p, okay? And p is supposed to live on the stack. So after we initialize the stack pointer, we need to decrement d in order to allocate that space for local variable p. So that means, from main's perspective, local variable p is supposed to be pointed to by the stack pointer directly. But I don't want to use the fact that the stack pointer points to local variable p, because if I change the program and I introduce additional local variables, the stack pointer may not be pointing to p anymore. So I don't want to rely on that fact. So instead, I'm going to define p as 0. Which basically means the offset to p is 0 from where d points to. Okay, so it is just an offset. So the offset it starts to make sense here after the decrement d instruction, because before the decrement d instruction, I have not yet allocated that space on the stack. Now that we have allocated that space on the stack, it makes sense. So we have to still do the call to f. Okay, so calling to f is LDI with 3, and then we have to push it on the stack, like so. So we are pushing 3 on the stack, and then we have to push the return address on the stack. So that's LDI dot 6 plus decrement d stda. So that's pushing the return address, and now we can continue execution at the subroutine, which is jmpi to the name of the subroutine, which is f. When the subroutine returns to where the cursor is at this point, we still have the argument sitting on the stack. So we have to do an increment d to deallocate the argument from the stack, and then we have to store the return value of f of 3 into p. So to do that, we don't want to shortcut things anymore. We don't want to say, oh, we know register d is supposed to be pointing to local variable p, because if I have additional local variables, where p is located can change relative to where the stack pointer points to. So from now on, we use a much more systematic way to do this, I would use a LDI. Cannot use register A because register A has the return value of F at this point, but B and C are free at this point. So I'm going to load P as a label into register B, which is really just putting a 0 into register B, in this specific case. And then we're going to add BD, which is adding the stack pointer to B. So once I combine the stack pointer and the offset from where the stack pointer points to the item that I want, now register B has the address of what I want, which is local variable P. So at this point, now the B is the address of P. I can just store to whatever B is pointing to, and register A has the return value from F of 3. So this will accomplish this statement in C over here. When that is done, I'm not ready to do a halt instruction yet, because at the end of every subroutine, we need to deallocate the local variables of the subroutine. So I have only one local variable, which is P, taking up 1 byte. So an increment D is going to deallocate the byte that I have allocated for local variable P, and at that point I can do a halt. So that's main. Now we go back to implement F. So once again, we want to know what the stack is supposed to look like from the subroutine F. So we know there is a parameter X sitting on the stack. Below that is a return address. And then below that, we're supposed to have local variable V over here. This is the frame. Okay, so this is what I call a call frame. Now it's okay, I take it back. It is not what I or TAC calls, as a call frame. This is what the industry people, the compiler people, refer to as a frame. You can call it an invocation frame, you can call it a call frame, or simply a frame. But it is called a frame because it is providing the context in order for a subroutine to execute. So the context of this particular subroutine F relies on the parameter X, the local variable V, and also the return address, so that it can go back to the caller. So these 3 bytes on the stack is important. And by the time I'm done with setting up the frame, the stack pointer should be pointing to local variable P, which it is not yet, okay? Because right now, after the caller is done, register D is currently pointing to the return address. I have not yet allocated for local variable V. So that means, upon the entry of this subroutine, I have to decrement the stack pointer so that I reserve the space for the local variable. So in this case, since I only got 1 byte, decrement D will do the job. Now this is also something that I usually do, is whenever I decrement, I automatically insert the increment, and also might as well include the return statement at this point, the return instruction, sorry. So I do LD B D increment D JMP B. Okay, so whatever I need to specify is going to be between the decrement D and the increment D. So in between, this is where I can actually write the code for subroutine F. Okay, this is where the body of F goes. Okay, there we go. Okay, no questions in the text channel, so I'm going to move on. All right, so now that we have everything done, I probably should update the picture. So basically, it's just a very slight change of the picture, because now the stack pointer is pointing to local variable V. So at this point, it is handy to use symbolic names or labels, so I can define V, my local variable, to have an offset of 0 from where the stack pointer points to. The return address is going to be 1 byte after that, and I'm going to prefix everything using the function name, so this way I can write multiple functions without having to worry about reusing the same label. So return address is 1 byte after V, and you can always just say, oh, it's just 1. But I'm not going to do that, because I'm going to say it is 1 byte past where I can find V. And now it's time to define the label X, which is the offset to where the parameter is. I can always say this is just 2, but that's not what I'm going to say. I'm going to say f return address 1 plus, okay, which is basically the postfix notation of return address plus 1. All right, so now that we have these labels defined, I am not going to use register C to move around to get to the item that I want, because that is, even though that approach is intuitive, because we can just increase it by 1, now we're getting to this item, we can decrement it once, and we can get back to this item. Even though it is intuitive in that way, it is not very scalable, because the moment I include, like, let's say if there's one more parameter here, it would just mess up everything, okay? And that's not good. Now, in this way, if I add any local variable or add any parameter, I do have to change the way these labels are defined, but the way I use the labels will remain the same. And that is the reason why I want to change from using register C to move around so I can get to different items in the frame, to using this much more systematic way of using symbolic names or labels, so that I can refer to a label and go like, okay, we know the offset from where the stack pointer points to. We just have to add the offset to the stack pointer at that point in time, and we can get to the address of those items that are in the frame of an invocation. All right, I'm just looking at the time. Okay, we got 7 more minutes. We got enough time. All right, so first thing is to get to the value of x, check whether it's 0 or not. Okay, so to do that, if we're going to do LDI, and A has no special meaning until we get to the return statement. So we can use register A, B, or C as quote-unquote general purpose registers at this point. So we're going to load it with the offset to x, which is f underscore x. And then we add the stack pointer to A, so A becomes the address of x. And we are not really that interested in the address of x, because we want to use the value of x and compare that to 0. So we need a LDAA. So A is now the value of x. Once again, I am verbally speaking out what a register contains, but it is up to you to annotate the code in order for you to. I'm giving you something to do, so that you mechanically will have to do something to help you understand the concepts. Okay. All right. So at this point, we want to compare that to 0. I could put 0 into another register and use a proper compare instruction, but we know there's a shortcut to do this, right? Because AND AA is going to force the value of A through the ALU without changing the value of A in the end, and still be able to test the flags, particularly the Z and the sign flag in this case. So after that, we do a JZI. If it is a 0, we want to get to the then portion. So we're going to go to the then statement of the only conditional statement in F. Otherwise, we want to go to the else statement. There we go. So now we define F then over here. At the end of this, we have to jump around the else statement to F and if. And then F else is going to be here. F and if is going to be here. So this is the way I code. I basically write down the structure of all the labels relative to each other, and then I backfill what I need to do for the then case and what I need to do for the else case. I found that if I don't do this, I would have trouble later on to figure out where those labels are supposed to go. But right now, because I have not filled in the extra code for each branch of the conditional statement, it is very easy for me to see where each label is supposed to go, including the unconditional branch to jump around the else case. So this is just a programming style. It's definitely not something that I use for grading. But if your programming style impacts, how effectively you can write your code, and how if it affects how easy for you it is to introduce bugs, then it does impact your grade in the end. Alright, so the then case says we just want to return a 1, but through local variable v. Okay, so this is really kind of unnecessary because I could have just put 1 into register A and make the assumption at the end that register A still has the return value already. But I'm not going to do that. I'm going to do a very literal translation of the C code here. So we want to store the 1 into local variable v. So how do we do that? Easy peasy. So I'm going to use register A, for the right hand side of the assignment. I'm referring to this assignment over here. And then we want to calculate where v is supposed to be at. So we have the LDI, cannot use A anymore. I'm going to use register B, f underscore v, that is the offset to v from where the stack pointer points to, add bd. So now b is the address of v, and now we can just do a store. So that's it. The else case, on the other hand, is a little bit more complex. So for the else case, I'm also using the indentation in assembly code so that I can reflect the nesting of the code that was originally presented in the C code. So this is quote-unquote structure programming in assembly code, just by using indentation so that I can understand, how it maps to the C code. Alright, so we need to push x minus 1 on the stack first, which means we need to get back to x. So LDI A with fx, add AD, so that A is now the address of x, LD AA, so that now A is the value of x. And then what we need to do is to decrement it once so that we have x minus 1, and then we push it on the stack. Decrement D, stda. So now we just push x minus 1 on the stack. It is time to push the return address, which is LDI A dot 6 plus decrement D stda. Now we have the return address already pushed. It is time to actually continue execution at the subroutine that we are calling, which turns out to be the same subroutine that we're in. Okay, that's just coincidental. It doesn't change the way that I call a subroutine. When we come back, when the subroutine returns, we have to deallocate the argument, so increment D, and now we have to compute the value of v. So that's just LDI, choose a register other than A, so we'll choose register B, FV, add BD, and STBA. So that will accomplish the first statement, and then we are going to do some very I'm just going to say very stupid thing because I'm doing a very literal translation of the C code, which is kind of the whole purpose, right? Because I want you guys to kind of get used to how we do this. So the right hand side of this plus equal to is just v, so we're going to do it all over again. Okay, so when you get this code, you need to annotate it, and if you feel that I'm bored because we're doing the same thing over and over, I get it already. Well, boredom in this case is a good thing because it reflects that you probably understand the concept. So at this point, we have the value of v in register A, and we want to add it to whatever v already has. So I'm just going to say add AA, so we double the value, and then we store it back to where v is supposed to be at. So this time we'll do LDIB FV, add BD STBA. So that should double the value of v. And now we get to fEndIf, which is to use local variable v as my return value. So one more time, I'm going to do LDI. Register A is fine. FV, add AD, and then we do a LDAA, because this time we are just trying to retrieve the value of local variable v. So this is how I retrieve it, and we are done. Okay, so after we are done, at the very end we have to do the increment D first to deallocate local variable v, because otherwise I'll be using the value of local variable v as my return address, which is not going to be pretty. I mean, I mean, one thing you can do with my program is to artificially try to introduce bugs. Just randomly, not randomly, but systematically remove statements, remove instructions, change the instructions, and see how it's going to mess up the program. Okay, so I am running a little bit over time, but it's all done. So let's go ahead and test this code to see whether it works or not. And this is in River Spider. There we go. Submit. It's called recursion.ttpasm. Alright, so we'll do a quick double check. I'm not very confident that this program will work the first time, but we'll see. So once again, we will basically check the last line first. It's going to be in summary. We know it's taking up 261 rows. So we go back to analysis. There we go. And go to row 261. Register D is the stack is balanced. It is back to 0, and 4A is indeed the halt instruction. So far so good. We also want to know whether an 8 is stored to location FF. So we want to check that. Yep. So there we go. So the in addition to annotating the code, which I'll supply to you, it is also useful to basically just kind of quickly go through the trace and see if you can understand what is going on, how the memory location on the stack are updated, how this trace also corresponds to my earlier demonstration using GDB in the C code, because the idea is the behavior of the program doesn't change. The way it's specified in C code and the way it's specified in assembly code, they are just different ways to represent the operations. What the logic is representing is identical. This is still the same program. Okay, so what it's doing to the local variables, to the parameters, the recursive call, they are happening exactly the same way in the assembly code as it did with the C code. So being able to look at GDB, understand how it happened in C code, and also looking at this trace here and understand how it happened in assembly language programming, that is what I want you guys to do. Okay, because I want you to make that association. That's basically the really useful part of this class, is now you have an X-ray vision into how your C code execute when you ran it. Okay, when you run your C code. Alright, so I'm done with this sample program. I will post the code. Okay, let me zip up everything first. Oh, wait, before I do that, let me release the lab for tonight. Before someone asks, do we have a lab tonight? Yes, we do have a lab tonight. I hate to be snarky, but sometimes I just am snarky. Alright, so this is call frame, and we are going to look at the passcode is framed, okay, and it's due tonight. I'll give you guys the 5 minutes back, 6 minutes back, so it's July 20th, 8:20. I'll give you 8:29. Okay, it didn't like it. Oh, because I forgot to specify PM. I wish they let me specify time in 24-hour format, but nope, doesn't want it. Alright, so the lab is released. I am going to zip up the code so I can post it into the text channel. And once again, it is super duper important, I think, to download that code, annotate, test it, just use it as a tool to understand the concepts. Yes, framed. Thank you, Paul. And so for the most part, I'm done. You can get started with the lab as I zip the code and post it in the text channel. But I'm still online. We're still doing live stream right now. So if you do have a question, please go ahead and ask the question now. All right, so we want to zip to recursion.zip, recursion.c, recursion.ttpasm, and I'm going to post the zip file. Yeah, I can hear people signing out, because Discord makes all the notification sounds. All right. And the file is recursion.zip. Nothing is happening. Oh, I forgot to click open. Alright, so let me do this one more time. /recursion.zip. And then have to click open. There we go. Alright, so you have the C and the TTP ASM source code. And for people who signed out already, when they ask me, about recursion and what is a frame and so on, I'm just going to say, but you signed out a little too early. Alright, so you guys have it now, and I am going to take a 10-minute break, and then I'll be back to answer questions if there are any. I'll see you. If you don't have any questions, I'll see you tomorrow.